everyone. I think we're going to start the second part of the morning. We will have a presentation of the BerkeleyGW project by Mauro Del Ben with the Lawrence Berkeley National Laboratory, and he's one of the lead developers of the code, and he will also be leading the national code under this. Thank you.
Thank you. Can you hear me? All good. All right. So thanks, Feliciano, and thanks to the organizer of this great summer school. We really had a great time, and it's just sad that it's almost over. And thanks, everybody, for being still here. I'm just the last one standing from here to your lunch break, so let's try to keep it short. I only have 74 slides. So I'm going to give you a short introduction, an overview of our software package, which was also introduced by Zhenglu in the previous talk, the BerkeleyGW software package, which is a massively parallel software package, which is employed to study the excited states properties of electrons in materials by using GW and GW plus Bethe-Salpeter equation. Now, we're going to have a tutorial in the afternoon. Here's the outline of my talk. I'm going to start with a short introduction, giving you the framework of why we are developing our software package, especially how we are developing to take advantage of massively parallel HPC system. Then I'm going to give you an overview of the software package and the main module, how we do implement the GW plus Bethe-Salpeter equation workflow in BerkeleyGW to finally summarize with the take-home messages. So we have just a short time this afternoon for the tutorial. Beginning of the year in January. So if you are interested in GW and BSc and BerkeleyGW, please join us. This is a picture before the pandemic when it was in person. We had a couple of virtual only tutorial, but we hope to resume the in-person tutorial starting next year. Now, short introduction. You probably already know that material science and chemistry application are among the most heavily used on HPC facility all over the world. And some of these names might be familiar with you: VASP, Quantum Espresso, of course, QMC-PAC, NWChem, BerkeleyGW, and CP2K. And the reason why these kind of software packages are so popular is that are very useful in order to understand and predict and study the electronic properties of electronic materials, which eventually are the kind of property you're interested in if you want to design new novel material for novel technologies. And here, just a list of the possible applications you can think about: quantum computers, batteries, photovoltaics, catalysis, energy storage and conversion, and so on and so forth. Now, for almost 3 decades, and up until now, and probably for another 3 decades, density functional theory has been the workhorse for this kind of application. And the reason is that density functional theory provides you with an excellent compromise between accuracy and computational efficiency. On the other hand, density functional theory is a ground state theory, as was stated before by Zhenglu, so often it's problematic and gives problem once you have to actually try to simulate excited states properties. And of course, this is a challenge once you are actually interested in excited states property. And this is an example, is a die vacancy defect in silicon. These kind of systems are now interesting because they serve as a proxy or prototype for solid state qubits. And as you can see, density functional theory provides you here with a decent description of the ground state, but often fail in the description of the excited states, so this empty part of the spectrum, which is actually the part that you are interested in once you try to design this kind of technology for future application. Now, this implies that you have to go beyond the accuracy of density functional theory in the direction, for example, of many-body perturbation theory, and in our kind of application, the GW and the GW plus Bethe-Salpeter equation. Now, the state-of-the-art GW and BSc probably represent one of the most effective and accurate approaches in order to study these kind of properties over a wide range of materials. So just recently, there have been a lot of interest, for example, to apply these kind of techniques also in chemistry for molecular and macromolecules. But yet, the application of GW plus BSc to routine calculation, as you usually do for density functional theory, is still kind of perceived as very complicated or not, or prohibitive, especially because of the increased computational cost. And this is kind of the goal of our developers team, is to push forward the GW and BSc in order for the user to be able to use this kind of methodology more and more commonly. In order to do so, we work at different level. we develop constantly new method and approximation, for example, to improve the accuracy and explore new physics, but as well to reduce the prefactor of the application in order to speed up the calculation, as well as in the long run, reduce the non-favorable scaling with system size from N4 to N3, and in the long run, linear scaling. We also work a lot on HPC optimization. We want to improve the performance of our application, not only in terms of parallel scalability, but also in terms of node performance, or gain traction out of GPU acceleration or accelerator in general. And this helps even moving forward the possibility that we can do right now, just exploiting the increased computational power every year. And as well, we maintain our software package in a well-tested and documented way, such that we can take advantage also from other developers which are outside our closed circle. Now, the BerkeleyGW software package, I already told you, is a massively parallel software package which is employed to study the electronic excited state properties of electrons in materials by using the GW and Bethe-Salpeter approaches and beyond. Our core kind of development or core business is actually focused on GW and BSc and beyond. So we don't really work at the DFT level. We take all the good kind of software packages which are around, and we convert their output into an input which is suitable for our format. So here's just a list of all possible software packages, but if you want, there's a detailed description on how you can interface your own code into a format that can be used by BerkeleyGW. We have this conversion layer that allows us to convert all these possible output into an input suitable for us. And then we can work directly on developing methods which are actually focused on excited state properties. So we have few main modules, 4 main modules, which implement the GW plus Bethe-Salpeter equation workflow, which I'm going to expand on. But the software package is shipped with many other tools that helps you, for example, for the pre or post processing, analysis of the data, visualization, and so on and so forth. Now, in general, highlights of the software package, I already told you, we interface with many mean field codes, so we can take all the advantages from these different software packages. We can support any kind of boundary condition, from the standard box system, the 3D boundary condition, down to reduced dimensionality, 2D, 1D, down to cluster or macromolecules, by actually having a specific modules to handle the kind of way we handle the Coulomb interaction among periodic images. We also have model for handling any kind of system types. So semiconductor, originally BerkeleyGW was developed as a semiconductor code, and recently we have expanded to metallic and semi-metallic system, as well as system with reduced dimensionality. And we often rely on external libraries, especially for pre-exascale and exascale kind of application, such that we can offload the maintenance of a complicated algorithm to a focus team. And finally, the code is massively parallel. We have demonstrated the capability to scale to hundreds of thousands of CPU or multi-core architecture, up to 500,000 on the KNL partition of Cori, and more recently also the capability to effectively leverage strong scaling on GPU accelerated system, being able to scale to more than tens of thousands of GPUs. Now, we have recently just deploy a newer release, a major release 3.0. There are a few things that you can do more compared to the previous one. New physics, we have enabled the full 2-component spinor support that enable the spin-orbit coupling spin-orbit coupling support for GW and BSc. We have introduced the exciton finite momentum Q, which allows you to plot exciton band structure. We have broadened the range of possible starting point, mean field starting point that you can start with from, including hybrid, meta, GGA, DFT plus U, and so on and so forth. We have also introduced for the first time the GPU support, especially for the Epsilon and Sigma module work, which is going to be completed in the next release 4.0 sometimes at the end of summer. And we have streamlined the IO workflow by moving completely on the high performance HDF5 library, which allows you to improve by order of magnitude the IO requirements for the entire workflow. We have new tools, and I think we're going to talk about this in the hackathon as well, to facilitate the wave function self-consistent calculation. And as well, we have improved performance, we have improved the tools, we have improved documentation, and as usual, fixed many bugs that were present in the previous release. Now, the workflow of the GW plus Beta-Salpeter equation as implemented in the BerkeleyGW is schematically shown here. We start from this large variety of mean field application, step 0. We convert into an input suitable for our software package. And then we have these 4 major modules, Epsilon, Sigma, Kernel, and absorption, which are interdependent, and the input and output generated by each of these modules can be reused by the other for various reasons. So the reason of having like multiple modules, well, there's first a reason is that is breaking down essentially the theory or the basic implementation into various steps. And each of these modules have a very different data structure, data layout, very different computational cost, very different kind of parallelization strategy and memory requirements. So breaking down the overall complex workflow in different steps allows you to effectively utilize HPC resources in the best way possible, depending on the type of the system or the type of calculation you're running. Additionally, some of the intermediates can be reused multiple times by other modules, for example, for check convergency, without having to rerun from scratch the entire workflow. Now, the first 2 modules, Epsilon and Sigma, are implementing the GW part of the workflow, and the kernel and absorption implement the second part of the workflow, which is the BSC, the solution of the Beta-Salpeter equation. And in today's tutorial, you're going to first run the GW for silicon, and then with the result of the GW result from silicon, you're going to calculate the optical spectrum again of silicon by using BSC. Now, to give you like a brief idea of what is each of these modules doing, Epsilon is generating the dielectric function or polarizability of the system. Well, it's connected with the polarizability of the system and its frequency dependence. And Sigma reading the dielectric function, inverse dielectric function, calculate the screen-Coulomb interaction and solve for the Dyson equation in order to calculate the quasi-particle states of your system. The output generated by these 2 modules, in particular the inverse dielectric function and the solution of the Dyson equation, are then plugged into the kernel, and the absorption, which first calculate Beta-Salpeter Hamiltonian kernel's matrix elements over a coarse K grid points, coarse grid of K points, and then absorption takes in the kernel's matrix elements, interpolate them on a fine K-point grid, builds up the Hamiltonian, diagonalizes the Hamiltonian, and gives you the optical excitation energy and exciton wave function. Now, this is not switching. I should have another slide. Okay. So before moving to give you more details about each of the modules, I want to actually introduce which are the basic computational kernels or computational motif that builds up the guts of BerkeleyGW. And the reason is that by understanding the kind of computational motif we are implementing will help you in order to decide, for example, how to optimally utilize HPC architecture or computational resources. Some of the basic structure are actually shown here. We perform a lot of large distributed matrix multiplication, for example, for the calculation of the polarizability matrix. We perform a lot of large distributed linear algebra, LU decomposition to perform low rank approximation, for example, matrix inversion, or eigen decomposition, eigen problem. That is basically the way we extract the exciton wave function out of the BSC Hamiltonian. We do, being a condensed matter code, of course, we do a lot of fast Fourier transformation, with the only difference that we can perform these node locals or embarrassingly parallel, especially for the calculation of intermediate matrix elements. So we don't have to deal with parallelization of this step. We also do dimensionality reduction, tensor kind of reduction, and low rank approximation, as previously mentioned. And also we are intense in parallel IO, especially for printing out, for example, the dielectric function or the BSC kernel matrix elements, so tensor rank 2, rank 3, and rank 4. Again, we have a hybrid level of parallelization. The original one, multi-node, which is now used for multi-node communication, is based on the MPI libraries. We have worked a lot to optimize our software package on many core architecture. So at the node level, we use the OpenMP programming model to share the workload over multi-core architecture. And recently we have introduced accelerator, so GPU acceleration, starting with CUDA, as mentioned in the talk yesterday, was the kind of programming model giving best performance on NVIDIA GPUs. But for the mainline development, we use the more portable OpenACC and OpenMP target as we prepare to transitioning to newer or to other kind of vendor GPUs such as the Intel and AMD. Now, to summarize this overview, the goal of our developers team can be summarized as 4 major pillars. The first one is to distribute a highly performant production quality set of tools, computational tools, that allows user to effectively being able to predict the excited state properties of electrons in materials by using GW, BSC, and beyond. We optimize our software components in order to run efficiently on pre-exascale and exascale system without actually leaving behind the small cluster or even running the software package on your laptop. So we make sure to optimize our software in order to be able to run efficiently on any kind of architecture. We integrate new features from developers all around the world in the package in a well-tested and production quality way. And we try to keep a close connection with our vibrant user and developers community, which actually help to drive even further the developments. Now, to give you a perspective of the kind of HPC optimization we are doing, here we are plotting the kind of system we have been able to tackle with the GW approximation over time. So you can see we started almost 30 years ago. Back then, we were able to treat only 8 electrons. And here we just report over time by optimizing our software package or to take traction of HPC, leadership class HPC system, how we have been able to expand systematically the capability of BerkeleyGW up to until basically a few years ago, where we have demonstrated the capability to scale up our application to more than 10,000 electrons running on the entire Summit supercomputer with the GPU accelerated partition and performing this calculation in order of tens of minutes. So if you want, by following this trend, we essentially are able to exponentially grow our capability by actually closely following the Moore's law that describes the increase of computational power over time. Now, more details about the various modules. Again, we are going to start with the GW part, Epsilon and Sigma. And as already previously mentioned, I'm going to just summarize a little bit what the GW is doing. Within GW, we actually calculate or extract the dynamical properties of the electrons by solving a Schrodinger-like equation, which is known as a Dyson equation. And the equation is given here. It's very similar to a Kornsham equation, with the difference that all the complicated quantum mechanical interaction among the electrons are described by an effective potential, which is known as the self-energy. So if you want, the self-energy serves like a very similar role as the VXC potential serve in density functional theory, with the difference that is a little bit more complex object, is a non-Hermitian operator, is non-local and frequency dependent. Now, in BerkeleyGW, we implement the solution of the Dyson equation. We break down the solution of the Dyson equation by breaking down the 2 major bottlenecks, which are implemented in the 2 standalone modules, Epsilon and Sigma. In particular, Epsilon compute the inverse dielectric function with asymptotic scaling, quartic asymptotic scaling with the system size. And then Sigma takes in the inverse dielectric function, compute a set of self-energy matrix elements in order to expand the Dyson equation, and then solve the Dyson equation at various levels of theory in order to get the quasi-particle correction. Now, in Epsilon, we take an input wave function, mean field energy, Q-grade width, and frequency. And the first step is to compute a set of matrix elements, which is essentially like an overlap between the conduction and valence wave function of the mean field application with an auxiliary plane wave basis, which is used to expand the polarizability and dielectric function. After that, we compute the polarizability and the frequency dependence. This is nothing more than a big matrix multiplication. So the core level, we implement this operation as a Z-gem, and this is actually the part which is the bottleneck of Epsilon. Once we have computed polarizability, we scale by the Coulomb potential, we invert the matrix, and we have the inverse dielectric function. Now, for a large-scale application, the evaluation of chi-0, so the polarizability of the system, is by far the computational bottleneck of the application. And this kind of operation is implemented as a large distributed matrix multiplication over short and fat matrices, as shown in the layout here. So to give you an idea for a large scale application, so when we are going to thousands of atoms, tens of thousands of electrons, this matrix is very, very big, is of the order of hundreds of thousands of rows and can easily exceed hundreds of millions of columns. We use we chop out the matrix with this parallel distribution, distributing the column of the matrix on the left, and we distribute instead with a 2D block cyclic distribution chi0, such that we can use, for example, scale-up library to perform the last step, which is the inversion. So we have a different strategy we have implemented in order to perform this step efficiently on HPC system. In particular, we have switched recently on what we call the non-blocking cyclic communication scheme. We might have like an exercise at the hackathon to play around with this communication scheme that allows to replace collective operation with non-blocking send and receive, organize it into a ring of communication in a way that the two nearest, communication happen only between nearest neighbor, and by desynchronizing the ZGEM call, you can effectively overlap the communication and the computation steps. Additionally, if you are interested in the full frequency calculation, you have to perform one of these matrix operation for all frequency. But recently we have introduced an approximation which allows you to greatly speed up the evaluation of the full frequency part of this of the epsilon matrix by using a low rank approximation of the static polarizability. And I'm going to expand about this in a later slide. Now, here's some of the performance. I told you about the capability of exploit the non-blocking cyclic communication to leverage massively parallelization. And here is shown the strong scaling measured on Edison at NERSC for 3 different systems of increasing size, silicon divacancy again, 214, 510, and 998 atoms. And you can see that we can exploit strong scaling over a wide range of node, up to 100,000 of cores, depending on the system size, and also achieving excellent time to solution of the order of tens of minutes. Recently, we have also introduced the GPU version. Time to solution went down by order of magnitude, and you can see here that epsilon for much larger system up to 2,700 atoms can effectively scale to tens of thousands of GPUs as well. All right, so epsilon, having done epsilon, let's move to sigma. And sigma compute a set of self-energy matrix elements, depending on system size, 100 to 1,000, in order to solve the Dyson equation. And there are different level of theory at which you can solve the Dyson equation. And I think Zheng Lu in the previous talk already covered some of these approaches. So in general, the expression for evaluating each of the self-energy matrix elements is given here. That implies an integration over frequency. And we have 2 different ways we can handle the frequency dependence in BerkeleyGW. The first one is the generalized plasma pole model, which is the default, use an analytical approximation for the frequency dependence. The advantage in this case is that requires only the evaluation of the static polarizability. So this is an analytical approximation. We can also actually carry out the full integration. This is called the full frequency model. We actually discretize the integral over frequency. We perform the integration numerically. We use a contour deformation techniques to perform the integral, but this required evaluation of the inverse dielectric function or polarizability at multiple frequency. And again, we have a method to speed up this step, and I'm going to talk a little bit about this later. So the parallelization strategy in sigma is quite straightforward. The evaluation of each of the self-energy matrix elements is largely independent on each other. So we are using a 2-level parallelization. The first one is an interpool parallelization, where we create pool of process, each working independently on a subset of self-energy matrix elements. Here is shown the example of 16 MPI tasks. We split in 2 pools of 8 process. The first pool is working on the first 2 self-energy matrix elements. The second pool works on the other 2 self-energy matrix elements. And then the complication about implementing the parallel version for the evaluation of self-energy matrix elements is only essentially happening within the pool, and this is what we call the intrapool parallelization. So here is the working equation for the GPP model. We have very similar working equation for the full frequency model, and here on the top we show the kind of data layout which is implemented. And if you want, from a pure computational standpoint, this is nothing more than a series of matrix vector multiplication followed by a dot product, where there's an interdependence between the matrix and the vector. So if you want for both model, the bottleneck for a single self-energy matrix elements is cubic scaling for both GPP and the full frequency. With the only difference with the full frequency, we have the prefactor of the number of frequency we have to carry the integration over, but the number of frequency doesn't depend on the system size, but depend on the system type only. So in principle, if you are just interested in the band gap or a few selected states, the entire sigma scale with the cube power of system size. If you need to correct a large number of quasi-particle energy in order to feed into the BSC part of the workflow, then increasing the system size, you also need to systematically increase the number of quasi-particle, meaning that the overall sigma will scale N4 if you are interested in actually doing then a BSC calculation. Now, some performance for sigma shown here. This is the result we have achieved by optimizing sigma in particular for KNL architecture, many core architecture, the KNL partition and NERSC. Here is shown that we are able to scale our application to the entire size of Cori back then. So it was more than 500,000 core. And we can also achieve excellent time to solution and high fraction of peak performance, 11 petaflop back then, which corresponded a little bit short than 50% of peak performance. So particularly good for this application. And here recently we also implement GPU support, of course, for sigma. Here is shown the performance we have achieved on Permater, which is the recently deployed GPU accelerated system at NERSC. On the left, we basically show that we are able to scale to the entire Permater. It's a 5600 GPUs. We essentially here shows capability to scale to 4800. We wouldn't have any problem to go up to 56 with a larger system. And more interestingly here, we are showing how we stand in terms of time to solution once we moved from the previous system, the Cori-Haswell partition, into the newer GPU accelerated system. If we take just a one-to-one node comparison, we observe a 76x improvement in time to solution. So this gives you an idea how important it is to fully take advantage of new architecture in order for your calculation to be performed more and more efficiently, or being able to perform more calculation or larger calculation than what you are currently able to do. All right, I was mentioning how do we speed up the evaluation of the full frequency. So the previous calculation were mainly talking about GPP approximation. In the case of full frequency, you have the complication that you have to evaluate the inverse dielectric function over multiple frequency in order to carry out the integration numerically. We have introduced a way to speed up this evaluation by using a low rank approximation of the static polarizability. We essentially diagonalize the static polarizability, and we use the eigenvector of the static polarizability as a new basis instead of the original plane wave basis. We can rewrite all the equation in order to exploit the subspace basis. And if you do that, you get an acceleration in the full frequency part, which is proportional with the square of the reduction in the number of the eigenvector used for the new approximation. So it's shown the evaluation of the GW full frequency band structure for silicon carbide. We are comparing here the full calculation, so without approximation, and the approximation, the static subspace approximation by using a screening threshold on the eigenvector of 10 to the minus 3. So if you want it correspond 5 10 to the minus 3, it corresponds to this calculation here. We are using 10% of the original number of eigenvector, and the time to solution goes down to essentially a 10% compared to the total time to solution. All right, GW part of the workflow is complete. I'm halfway to the talk, so let's talk about the BSC part of the workflow. That means kernel and absorption. Now, to put this in a very simple term, what we are doing in BSC is to essentially solve a big eigenvalue problem. And you are interested into the excitation energy and exciton wave function, and you start building this big Hamiltonian from something that you already have calculated. So what you have is actually the GW quasi-particle eigenvalues, which correspond to the diagonal part of this matrix. And then you have the electron hole interaction kernel, which is this dense matrix, which is computed by kernel, by the way. And once you solve the BSC equation, you get, again, the excitation energy, omega s, and the exciton wave function, which are the coefficient of the eigenvector solution of this problem. And these kind of quantity are anything you need in order to calculate all the properties you are interested in. For example, the exciton wave function in real space, the optical response spectrum, and so on and so forth. Now, very similarly to the GW part of the workflow, also in this case, we can recognize two major bottlenecks in the evaluation of the solution of the BSC equation, which similarly to the case of the GW part of the workflow are implemented in two standalone modules. The first one is kernel. Very originally, kernel is computing kernel matrix elements on a coarse K grid and display computational cost would grow with the fifth power of system size. And then absorption takes in the quasi-particle computed from the sigma, so from the GW part of the workflow, takes in the kernel matrix elements computed by kernel and interpolate those onto a fine grid of K points, build up the Hamiltonian, the BSC Hamiltonian, and just diagonalize that to get the excitation energy and exciton wave function. Now, kernel has very similar feature as what we find in terms of computational kernel with sigma and epsilon, actually. And we distinguish two different kinds of kernel matrix elements, the screen direct interaction and the Baire exchange interaction, which sum up in order to build the BSC Hamiltonian. So again, we recognize very similar structure in the evaluation of intermediate matrix elements between conduction valence block, valence block, and conduction block with an auxiliary plane wave basis. And again, this auxiliary plane wave basis is the same basis you have used in order to expand the polarizability, inverse dielectric function, and eventually the screen Coulomb interaction. And then you calculate the screen direct and the Baire exchange matrix elements. The screen direct term eventually is just contracting your original matrix elements by using Z-gem and dot product, also displaying an N5 scaling with system size. And the exchange term is very similar to the direct term, with the difference that now we have the diagonal representation of the Coulomb potential rather than the screen Coulomb interaction. Also, in this case, it's essentially a series of dot product, so also scaling with the fifth power of system size. So some parallelization trick for kernel. We have a multiple level of, well, different parallelization strategy implemented in kernel depending on the number of MPI tasks you're using. The first attempt is to parallelize over K points. This happens if your number of process that you're using is smaller or equal to the square of the number of K points you have in the calculation on the coarse grid in particular. So the optimal number of MPI tasks you would use in this case is equal to the square of the number of K points. The second attempt, if you exceed this number, you have more computational resources, is to distribute pair of K and conduction band. In this case, the optimal number of MPI tasks you want to use is the square of nk times number of conduction band. And similarly, if you have a huge machine, you can actually distribute the entire triplet of K points, conduction band, and valence band. And again, optimal number of MPI tasks would be the square of this number, which of course is huge if you have even a relatively small system. Now, we have two important keys that you can use in order to save computational time or to save in terms of communication. One is called high memory. This allows you to store intermediate wave function FFT transformed into the real space. This is memory consuming, but allows you to greatly speed up the evaluation of the matrix elements given in one, because you pre-compute the outermost loop, and you can reuse the transform FFT in the most inner loop several times. The other key that is important in order to save communication is what we call low com. Again, it's low com, but require high memory. What it's doing is to replicate the screen Coulomb interaction, if you want, on each of the MPI tasks, such that this doesn't need to be communicated among MPI tasks, and essentially becomes the entire computation of kernel's matrix elements embarrassingly parallel. Now, absorption is executing this interpolation. The reason is that exciton depends critically on the K-point sampling, and Zheng has already mentioned this in the previous talk with some of the example. So this implies that you really need a fine K-point grid. The problem is that evaluating quasi-particle self-energy matrix elements is very expensive, and computing kernel matrix elements is also very expensive. So this is the trick. We compute those expensive quantities on a coarse grid, and then absorption reading this quantity and interpolate them on a fine grid in order to solve efficiently the BSC equation. Now, I'm not going to go too much in the technicalities. I think we're covering this in the tutorial. The interpolation is based on the overlap metric. We compute the overlap between the coarse and the fine K grid, and we use those as a weight in order to compute the fine grid kernel matrix elements and also the quasi-particle energy. And this interpolation will be used also by in the tutorial in order to calculate the band structure. And here is just the result showing essentially the interpolated band structure for single-walled carbon nanotubes, the BSC band structure obtained after these interpolation steps, so essentially number 3. So very similar techniques can be actually applied for the kernel in order to compute fine grid kernel matrix elements and build up the BSC Hamiltonian. Now, again, the bottleneck in Epsilon, in the absorption, is going to be the diagonalization of a large matrix. The size of the matrix grows linearly with the number of valence bands in the calculation, linearly with the number of bands in the conduction band, and linear with the number of K points. So you take the product of these 3, and you get the size of your matrix. Formally, it's scaled with N6, even though NK is inversely proportional to the supercell size. And we can use various libraries. We interface with, for the exact diagonalization, of course, with Scale-Apac, but also with ALPA, which can gain traction from GPU acceleration. And in the hackathon, we're going to play a little bit with those algorithms and for you to understand how those scale and understand how much resources you need to allocate in order to run this application for an arbitrary matrix size. We also interface with the iterative solver, the prime library, which allows to extract only a smaller fraction of the total number of eigenvectors if you are just interested in the lower part of the spectrum and not in all excitation. And also we have implemented the Hajduk reduction, which is a method which reduces the computational cost to N4, but it doesn't give you the full information. It's essentially restricting the information to compute the absorption spectra. So it's essentially the shape of the absorption spectra. Now, since we have been talking about diagonalization, before summarizing the talk, I would like to introduce some of the recent tools, software modules which we have, which is actually delivered together with the software package, which is the Paraband tools. And if you want, it stands in between the mean field and the beginning of the GWBSC workflow. So in many times, one of the complaints that we received is that it's very difficult to generate a large number of empty states as required in order to converge GW and BSC. And this is essentially the nature of the iterative solver. They work very well if you're interested in a lower part of the spectrum, 5%, 10%, but they often fail if you need 50 or 60 or more % of the entire spectrum. In this case, direct solver are the solution. And this is why we have generated this Parabands tool, which allows you to extract a large number of eigenpairs just performing a straight diagonalization of the dense Hamiltonian. So if you want Parabands, build up and diagonalize the density function tier Hamiltonian, can build up as well the hybrid. It doesn't matter which kind of functional you're going to use. The diagonalization will have the same cost regardless of the functional. Builds up in plane wave basis, and then use a direct solver in order to perform the straight diagonalization. It takes an input, the quantum espresso, using the PW to BGW tool you're going to use also later in the tutorial. A wave function file, which is used for comparison to compare the eigenfunction or eigenvalues with the original eigenvalues. The Kleinman bilander non-local projector to build up the Hamiltonian, and the self-consistent potential in G space. So we support various libraries, again, very similarly to the case of absorption. We have interface with the Scale-Apac, ALPA, and Prime library. We can massively parallelize the code by distributing the workload over K points, and the K points distribution is embarrassingly parallel. We have implemented the way of outputting the wave function by directly using the high performance IO library HDF5 that you can directly use to start the GWBSC workflow. And then we have fully supported this this code to leverage many core architecture like the core kernel partition, and we are working on the GPU implementation right now, even though we can essentially use the ELPA library to offload this kind of operation on GPUs. Some reference timing, if you're interested here, we actually measured this timing on KNL on the left, and more recently we have done the same kind of test on the Core GPU, sorry, on the Perlmutter GPU partition by using the ELPA accelerated library, and you can see that you can pretty much diagonalize a very large matrix, 150,000 by 150,000, in something of the order of just 5 minutes by using the GPU accelerated system. So this bottleneck is becoming less and less of a bottleneck, and then we can focus more on the GPU, on the GW part of the workflow rather than just generating a bunch of empty states. All right, let me summarize my talk and also give you an idea where the developers team is moving as we step into the exascale era. So I gave you an overview of the BerkeleyGW software package that you're going to use later during the tutorial. I gave you an idea of the basic algorithms, parallelization strategy we have implemented, and the core computational motif which implement the entire workflow. And more specifically, I gave you some details about the 4 major modules. Epsilon, again, generated the dielectric function and the frequency dependence of the dielectric function. Sigma takes in the dielectric function, compute the screen Coulomb interaction, solve the Dyson equation at various levels of theory in order to provide you with quasi-particle energies, and then kernels compute BSC matrix elements on a coarse grid, and then absorption takes all the thing you have computed before, interpolate on a fine grid, builds up the BSC Hamiltonian, diagonalize the BSC Hamiltonian, and give you the excitation, energy, and exciton wave function. Some useful resources. We have an online manual, which is very useful. It allows you to dig into the various input feature and the various kind of method which are implemented in the BerkeleyGW. It's supposed to be very simple to use and also straight to the point. So it's intended to be working well for both beginner and expert user. And as usual, we have our BerkeleyGW mailing list. You can mail in any of your question or problem, and we try to help you as best as we can. If you are more interested in the kind of implementation or details about the actual CPU, well, the actual software implementation on various HPC system, here's a few papers. The original MPI implementation with the overview of the software package by Jack, and then the work we have done on multi-core OpenMP parallelization for, again, multi-core architecture, and more recently also the work we have done for the GPU support. And to finalize the talk, I want to give you here the kind of work we are doing in order to exploit GPU accelerated system on the path to exascale. Again, we already have like an exascale system in the US, which is Frontier, 1 point something exaflop. And we have specifically optimized our software package to gain traction on GPU. And recently we have been able to show parallel scalability, effectively using strong scaling on Summit to more than 27,000 GPUs, high fraction of peak performance, more than 50%, 53%, and 106 petaflop for our calculations. So yesterday was mentioned Frontera is a machine with peak performance of 40 petaflop. So in order to perform this calculation, you need 2.5 Frontera working at peak performance in order to replicate this kind of calculation. And again, excellent time to solution, order of tens of minutes for tens of thousand electron system. And this work was also nominated as a Gordon Bell finalist in 2020. And this is where we took on to deliver to the user our best GPU implementation for the future architecture. And with that, I think I'm still in the boundary of the time, but a little bit earlier, but I'm very happy to take questions and also to make some space for the final remarks. So thank you, and looking forward for your question.
I was wondering if BerkeleyGW currently, if the GPU implementation takes advantage of the relatively recent tensor cores that are in modern NVIDIA GPU or the AMD equivalent.
Right. So we don't specifically, I mean, we have done some work to try to take advantage of tensor core. There are two things. We mainly work with ZGEMs, so parallel matrix multiplication, FFTs, and a specific kernel that can take advantage out of tensor core might be the GPP kernel. So I didn't give much details about the tensor core, the tensor kind of reduction we do to calculate the GPP kernel. But what we have found is that using our own specific implementation and optimizing our specific implementation was giving much more satisfactory and performance result than trying to actually interface to the tensor core library.
Interesting. Thank you. Any other questions?
Thank you. Why don't we use launches approaches because the microcontroller?
So I'm not sure if so prime is this library that contains a lot of possible algorithm to do the diagonalization. I think we have a module to do launches approximation, but I have to double check. I'm not sure if we have released the method officially, but we were trying to move more in the direction of using external libraries, so we don't actually need to maintain our own implementation, and we focus on something else in the code. But yeah, definitely we can have a look and then let's see if we can. I'm not 100% sure what Scalapack is using in terms of algorithm, but launches is for sure one of the possibility that we can exploit.
I have just one question. Is it possible in BerkeleyGW to do self-consistent process to calculate the waveform?
So it's definitely possible. We're gonna have like maybe a tutorial of the hackathon to show, not that, but it's not implemented in the code, but you can use some post-processing tools in order to update the wave function and restart the calculation. So if you want, you can use like the Sigma module in order to, like an external library, if you want, to perform the update of the wave function and the eigenvalue to do the self-consistent approach.
We have a technical question. When you look at the selecting the amount of every matrix, just try to compare how that kind of fares with respect to just reducing the cutoff of every matrix.
Do you mean for the full frequency? Yeah, so we did so we considered them to be like interconnected kind of convergence parameter. What we found is that the accuracy, where is it? Yeah, so the accuracy depend essentially on the threshold on the eigenvalues. So if you set like a 10 to the -3, let's say, you diagonalize the polarizability, you select all the eigenvector which are above 10 to the -3 as a lower rank approximation. If you increase the cutoff of the matrix, the fraction is gonna increase, but the threshold, if the threshold stays the same, the fraction is gonna increase. So the two things grows proportionally. So you can clinch, if you want, the number of eigenvector you use with the screen cutoff by using this threshold that allows you to select the eigenvectors or eigenvalues and eigenvector pairs.
So I mean, I could do a calculation that a lower cutoff in that case?
No, because it converges differently. So you need a high cutoff because you need to match the cutoff of the wave function. So, and the eigenvector just linear combination of all possible, the waves that gives you like the lowest, gives like the eigenvector of polarizability. So it's very similar to what, if you want, Julia Galli and West is doing in order to extract like what they call it p-depth basis, right? So they are eigenvector of the polarizability they use as a new basis to expand the frequency dependence. We are doing something very similar, but the number of eigenvector grows grows proportionally, but you need to increase the cutoff in order to match, if you want, the kind of spikes you have in the wave function.
Thank you. Question? Anyone too? Okay.